Right now, as you sit there, listening, breathing, not thinking about anything unusual, something extraordinary is happening. Trillions of particles are passing through your body, not around you, not near you, through your skin, through your bones, through every atom that makes you who you are. And yet, you feel nothing, no warmth, no pressure, no sensation at all. They come from the heart of the sun, born in nuclear reactions deeper than any human will ever reach. They come from distant stars that died long before Earth even existed. Some of them have been traveling since the very first second after the universe began. They move at nearly the speed of light. And not one of them stops for you, not one. This is the neutrino, often called the ghost particle, not because it's supernatural, but because it behaves as if the entire universe isn't really there. Tonight, we're going to understand why, but not in a rushed, complicated way. We'll move, slowly, step by step, letting each idea settle, because the truth is, the neutrino isn't just strange, it quietly reveals something much deeper, that the solid world you trust, the world you feel, isn't as solid as it seems. So before we go further, let your body relax, let your thoughts slow down, and let's begin with something simple. Why can you touch anything at all? You press your hand against a table, and it stops. It feels solid, real, unmoving, but what's actually happening there is far stranger than it seems, because at the deepest level, nothing is truly touching. Everything around you, your body, the air, the table, is made of atoms, and atoms are mostly empty space. Imagine this. If an atom were the size of a football stadium, the nucleus would be a tiny marble sitting at the center. Everything else, the entire stadium, would be empty. The electrons, they'd be like tiny insects buzzing far out in the stands. That means the world you experience as solid is almost entirely nothing. Your body is almost entirely nothing. So why can't your hand pass through the table? The answer isn't solid matter blocking solid matter. It's a force, the electromagnetic force. When your hand approaches the table, the electrons in your skin repel the electrons in the surface of the table. They push against each other, without ever truly touching. That resistance, that invisible push, is what you feel as solid. It's not contact, it's interaction. Every texture you've ever felt, every object you've ever held, every step you've ever taken, is the result of this invisible force, an illusion that behaves perfectly like reality. And this is where things begin to shift, because the neutrino ignores that force completely. To understand why neutrinos pass through everything, we need to zoom out, because the entire universe, everything that has ever happened, is governed by just 4 fundamental forces. Only 4. The first is gravity, the one you know best. It keeps your feet on the ground, holds the Earth in orbit around the sun, and binds entire galaxies together across unimaginable distances. But despite how powerful it feels, gravity is incredibly weak. At the level of tiny particles, it's almost irrelevant. The second force is the electromagnetic force. This is the one that truly shapes your everyday reality. It controls atoms, chemistry, light, electricity, even the signals in your brain. It's the reason objects feel solid, the reason you can see, touch, and interact with the world at all. Without it, matter wouldn't hold together in any familiar way. The third force is the strong nuclear force. This one is different. It operates only at extremely small distances inside the nucleus of an atom. And yet, It is the strongest force in existence. It holds protons together, even though they should repel each other violently due to their positive charge. Without it, atoms heavier than hydrogen couldn't exist. No carbon, no oxygen, no life. And then there is the fourth force, the weak nuclear force. Unlike the others, it doesn't hold things together. It doesn't push or pull in the way you might expect. Instead, it allows particles to change, to transform from one type into another. And this is the only force that neutrinos truly respond to. Out of the four forces that shape reality, neutrinos essentially ignore three of them. Now imagine what that really means. A normal particle, like a proton or an electron, is constantly interacting. It feels forces, it pushes, it pulls, it reacts. It is part of the busy, noisy structure of reality. But a neutrino is different. It has no electric charge. That means the electromagnetic force, the force responsible for light, touch, and almost everything you experience, has no effect on it at all. It also doesn't feel the strong nuclear force, so it can't be trapped inside atoms or nuclei or anything like that. And gravity? Technically yes, but its mass is so unbelievably small that gravity barely matters. So what's left? Only the weak force, a force so limited, so short-ranged, that it barely reaches beyond the tiniest scales imaginable. This means something profound. For a neutrino to interact with anything, it has to come incredibly close. Not just close like atoms touching, closer than that, closer than the nucleus itself, closer than almost anything you can imagine. And most of the time, it doesn't. It simply passes through atoms, through walls, through planets, through you. Not because it's fast, not because it's trying to avoid interaction, but because the universe gives it almost no way to interact at all. And that's what makes it a ghost. Not invisible by magic, but invisible by design. To really understand the neutrino, we need to understand probability, because at the smallest scales of reality, nothing is guaranteed. Everything is about chance. Physicists describe this using something called a cross-section. It sounds technical, but the idea is simple. It's the chance that a particle will interact. Imagine throwing a ball at a wall. Easy to hit, right? Now imagine throwing that same ball at a single needle standing in a field. You could throw for hours, days, years, and never hit it. The needle exists, but the chance of hitting it is almost zero. That's what a neutrino interaction is like, except far more extreme. For most particles, the target is relatively large. Photons, for example, interact easily. That's why light gets absorbed, reflected, or scattered all the time. But for neutrinos, the effective target size is unbelievably small. So small that it's almost meaningless to think of it as a target at all. When scientists calculate it, the probability of a neutrino interacting with matter is so tiny that even writing the number feels absurd. It's not just unlikely, it's almost impossible, and yet not quite zero, and that not quite is everything. Let's take that idea and stretch it to something you can feel. Imagine a neutrino flying straight through the Earth, from one side all the way to the other. That's about 12,700 kilometers of rock, metal, and extreme pressure, an entire planet in the way. What do you think happens? Does it slow down? Does it bounce? Does it interact with something along the way? Almost never. The chance that a single neutrino will interact while passing through the entire Earth is about 1 in 10 billion. about that. A particle travels through a solid planet, and there's only a tiny chance it will hit even a single atom. Now take it further. Imagine a wall made of solid lead, not a normal wall, a wall that stretches for a full light year, nearly 10 trillion kilometers thick, dense, packed, unbroken. Surely that would stop them, right? No. Even then, about half of the neutrinos would pass straight through. Half! As if the wall wasn't really there, and this is where it becomes clear. The neutrino isn't phasing through matter. It's not ignoring reality. It's simply moving through a universe where the odds of interaction are so small that matter becomes effectively invisible. Now that you understand how unlikely interactions are, we can finally see the full picture. Because neutrinos aren't rare, they're everywhere. Right now, the biggest source around you is the sun, deep in its core, at temperatures of about 15 million degrees. Hydrogen atoms are constantly fusing into helium. Every second, unimaginable numbers of these reactions are happening, and with many of those reactions, neutrinos are created, not a few, not millions, roughly 200 billion neutrinos. Every single second, they burst out of the sun's core and stream into space in all directions. 8 minutes later, some of them reach Earth, and even after spreading out across that vast distance, the number that reaches you is still staggering. About 65 billion neutrinos pass through every square centimeter, every second. Hold up your thumb. That tiny area just had the tens of billions of particles pass through it, and they didn't stop there. They passed through your skin, your bones, your entire body, and kept going, straight through the earth itself. At night, when the sun is below you, those same neutrinos are coming up from beneath your feet. They've already traveled through the entire planet, just to reach you, constant, silent, unstoppable. And the sun is only one source. Neutrinos are coming at you from all directions, all the time. High above you, cosmic rays crash into the atmosphere. These are particles from deep space, moving at incredible speeds. When they hit atoms in the air, they create showers of new particles. And among those, more neutrinos are born. They rain down constantly, some from above, some from the other side of the planet, passing through the entire Earth before reaching you. Even the ground beneath you is a source. Deep inside the Earth, radioactive elements are slowly decaying. Uranium, thorium, potassium. Each decay releases energy and often a neutrino. So even without the sun, you would still be surrounded. And then there are the extreme events: exploding stars, collapsing cores, black holes feeding on matter. These violent moments in the universe release enormous bursts of neutrinos, and those neutrinos travel for thousands, millions, even billions of years, until, by pure chance, a few pass through you. And finally, there are the oldest ones of all, neutrinos born just 1 second after the Big Bang, still drifting through space, still passing through everything, including you, right now. You are not just in a universe filled with matter. You are in a universe filled with motion, an invisible storm of particles flowing through you without ever saying hello. At this point, a question naturally appears. If neutrinos almost never interact, how did we ever detect them? How do you observe something that refuses to leave a trace? The answer is patience and scale. Imagine flipping a coin, but it only lands on heads once every 10 billion flips. If you flip it once, nothing happens. 1,000 times, still nothing. 1,000,000 times, nothing. But if you flip it enough times, eventually it must happen. Neutrino detection works exactly like that. You don't try to catch one neutrino. You expose an enormous amount of matter to an enormous number of neutrinos, and you wait, not seconds, not minutes, sometimes years, because eventually one of them will interact. But there's a problem. The world is full of noise. Other particles, radiation, cosmic rays, all constantly hitting your detector, creating signals that look almost identical to what you're trying to find. So how do you filter that out? You go underground, deep underground, hundreds, even thousands of meters below the surface. The earth itself becomes your shield. Most particles are stopped by rock, but neutrinos, they pass straight through. So deep underground, in the quiet, you create a place where almost nothing can reach you, except the very thing you're trying to detect. One of the first successful neutrino experiments looked almost ridiculous. No futuristic machines, no glowing reactors, just a massive tank filled with cleaning fluid. This experiment was built deep underground, in an old gold mine in South Dakota, hidden beneath the layers of rock, far away from interference. Inside that cavern sat a tank containing over 600 tons of liquid, ordinary dry cleaning fluid, but chosen very carefully, because within that liquid were atoms that could, on rare occasions, react with a neutrino. When that happened, one atom would transform into a different element, just one, out of trillions upon trillions, and that was the entire signal. Think about that. You have hundreds of tons of liquid, and you're trying to detect a handful of atoms created over days or weeks. It's like trying to find a single grain of sand in an entire building filled with sand. And yet, they did it. They developed methods to extract those atoms, count them, and prove something incredible. Neutrinos from the sun were reaching Earth. The ghost was real. But there was a twist. They weren't seeing as many neutrinos as expected, not even close, and that mystery would take decades to solve. The experiment worked. Neutrinos were being detected, proof that these ghost-like particles were real. But something wasn't right. The numbers didn't match. According to everything physicists knew about the sun, about nuclear fusion, about energy production, a certain number of neutrinos should be arriving at Earth. But when they measured it, they only saw about 1/3 of that number. 2/3 were missing, not hidden, not delayed, just gone. This became known as the solar neutrino problem, and it wasn't a small issue. It challenged something fundamental. Either our understanding of the sun was wrong, or our understanding of physics itself was incomplete, and both possibilities were uncomfortable. The models of the sun were extremely precise. They correctly predicted its brightness, its temperature, its structure. It didn't seem likely they were wrong by such a large margin, but the data was consistent. Year after year, experiment after experiment. The results stayed the same. Only 1/3 of the expected neutrinos were being detected, and no one could explain why. For decades, this mystery remained, quietly sitting in physics, waiting for an answer. To solve the mystery, physicists needed better evidence, not just hints, not indirect measurements, but clear, undeniable proof. So they built something much bigger, much more sensitive. Deep underground in Japan, inside a mountain, they constructed an enormous detector, a vast tank filled with 50,000 tons of ultra-pure water, so pure that even the smallest impurity was removed. Surrounding it, thousands of incredibly sensitive light detectors, watching, waiting. Because when a neutrino does interact, it creates a tiny flash of light, almost nothing, but enough to be seen. This detector, known as Super Kamiokande, did something brilliant. It didn't just count neutrinos, it tracked where they came from. Some neutrinos arrived from above, traveling a short distance through the atmosphere. Others arrived from below, after passing through the entire Earth. If neutrinos didn't change, both groups should look the same, but they didn't. The ones that traveled further were missing, not completely, but noticeably fewer, and the longer the journey, the more disappeared. This was the key. It showed that neutrinos weren't vanishing, they were transforming, changing into forms that the detector couldn't easily recognize. The ghost wasn't disappearing, it was changing its mask, but one question remained. Were neutrinos truly missing, or just changing? To answer that, physicists needed a detector that could see all types of neutrinos, not just one. So they built another experiment. Deep underground in Canada, inside a nickel mine, they constructed a detector using something rare and valuable, heavy water. Water where hydrogen atoms are slightly heavier than normal. This allowed them to detect neutrinos in two different ways. One method could only see electron neutrinos. The other could detect all flavors equally. The logic was simple. If neutrinos were disappearing, both measurements would show fewer particles. But if neutrinos were transforming, then only the electron count would drop, while the total number would remain the same. And when the results came in, the answer was clear. Electron neutrinos were missing, but the total number was exactly as predicted. Nothing was gone. Everything was still there. The neutrinos had simply changed form along the way. This experiment, known as the Sudbury Neutrino Observatory, finally solved the mystery and confirmed something revolutionary. Neutrinos have mass, tiny, almost unimaginably small, but real. And with that discovery, one of the longest standing problems in physics quietly disappeared. In 1987, something extraordinary happened. A massive star, far beyond our galaxy, reached the end of its life. In a fraction of a second, its core collapsed, and then it exploded, a supernova, an event so powerful it briefly outshines entire galaxies. But the most important part wasn't the light, it was what came before. Because when that star collapsed, it released an unimaginable flood of neutrinos. Not millions, not billions, but around 10 to the power of 58 neutrinos. In just a few seconds, they escaped instantly, passing through the collapsing star as if it wasn't there, traveling across 168,000 light years of space straight toward Earth. And when they arrived, a few of them were detected, just a handful, around 24 interactions in detectors across the world. That's all, but it was enough, because those neutrinos arrived hours before the light. They carried the news of the explosion, before the explosion itself became visible. Think about that. Particles that barely interact with anything became the first messengers of a dying star. They told us what happened deep inside the core before any telescope could see it. It was the moment neutrinos stopped being just a curiosity and became a new way to observe the universe, a new sense, a way to see the invisible. And now we return to where we began, right here, right now, as you sit listening, breathing, those same particles are still passing through you, from the sun above, from the earth below, from distant galaxies and ancient explosions, even from the very beginning of the universe itself, roughly 100 trillion neutrinos, every second through your body, silent, unstoppable, untouchable. They don't know you exist, they don't feel you, they don't interact with the world the way everything else does. And yet, you understand them, you followed their story, from a desperate idea to save the laws of physics, to one of the most important discoveries about reality itself. A particle that barely interacts has taught us about the sun's core, the death of stars, the structure of the universe, and even hints about why anything exists at all. That's the quiet beauty of this. The universe created something almost invisible, and somewhere, on a small planet, it also created something that could notice. So tonight, as you drifted towards sleep, remember this: you are never truly still. You are part of a constant, invisible flow, a universe moving through you, without resistance, without effort, without end. And now, you know it's there. If you enjoyed this kind of calm, deep exploration, make sure to subscribe to Science Sleep Theory, and I'll see you in the next journey. Good night, and sleep well.